Professor Chad Mirkin is the director of International Institute for Nanotechnology, and George Glassman, the professor at Northwestern University. He has authored over 840 manuscripts and over 1,200 patent applications worldwide. And he served for 8 years on the President Council of Advisory on Science and Technology, and he is one of the very few scientists to be elected to the all three U.S. National Academy. And Professor Mirkin is a founding editor of the journal Small. Please welcome Professor Mirkin.
Okay, great. Thanks for the invitation to come tell you a little bit about what we're doing at Northwestern, focused on trying to develop a way to accelerate materials discovery. What I thought I would do is we're involved in a major collaboration with Toyota focused on trying to really, as I said, develop techniques that allow you to accelerate how we discover materials that can make an impact in many different fields. In the case with Toyota, we're focused primarily on the development of tools that will allow us to discover materials that can impact the automotive industry, and in particular, clean energy. So you have to bear with me. What I'd like to do, if you hopefully you could hear it, I'd like to play a 5-minute video that'll kind of set the stage for what I want to talk about in terms of the detailed science.
Meeting the growing demand for mobility without relying on fossil fuels is really one of the main challenges that we're facing. And we have to do this globally and for the whole transportation sector, not just cars. For this goal and for this challenge, discovering, designing, developing new materials is really critical.
Toyota depends upon new materials for all sorts of different purposes. You think of catalytic converters, fuel cells, the materials within those make them either efficient and useful or not. Being able to find the best materials is absolutely essential. I would argue that the world right now has been focusing on the best that they've discovered to date, and not necessarily the best for a given application. So what we're poised to do through the collaboration with Toyota is to begin to look at the vast parameter set possible in terms of materials discovery, collect data from that, and then empower machine learning and AI algorithms to allow us to objectively search the materials genome and find the best materials for a given need.
Before we were using machine learning, all of our materials design was trial and error. So we had to synthesize one material and then characterize it, and then synthesize this one and characterize that, and hope that any one of those we couldn't ahead of time.
Traditionally, we've pursued new ideas by human intuition. The things that scientists think might be interesting, they have some idea that they want to try out. By the kind of technologies that we're leveraging here at Northwestern University, it allows us to go beyond that, because not only can we use our intuition, but now we have the possibility of looking at a vast number of things that would not be possible otherwise. And that helps us look for things that we might not have thought of.
Every element has its unique properties and is different from every other element. And combinations of elements will interact with each other. Their electronic structure is influenced by the atoms around it. So depending on what they are, you can end up with a material that has vastly different properties. It can form different crystal structures. It'll have different surfaces, different electronic structures. And so there's a lot of space that has never been explored as to what the properties of these materials might be.
So the Megalibraries are really a product of the modern age of nanotechnology. We invented a whole series of what we call nano printers here. Think of a printer. It's got a print head that has 100,000 or more pyramidal tips. Those can be coated with chemicals, gradients of chemicals, and then brought down, and those materials can be deposited onto a chip of interest. Being able to control particle size and shape on the nanoscale within the context of a megalibrary is very important, because many of the active catalysts that go into fuel cells, that go into catalytic converters, that are used for catalyzing all of the important processes out there are nanomaterials. 1 nanometer would be, take a dime, slice it on edge 1,000 times. Take one of those pieces, slice it another 1,000 times on edge. That's 1 nanometer thick.
Nanoparticles have very unique properties in terms of their catalytic activity. They make for good catalysts because they have a high surface area to volume ratio because they're so small. So ideally, when we make nanoparticles, we're able to make particles that have a lot of available surface for catalyzing reactions and use less of a valuable material like platinum, for example, that goes into a fuel cell. The more active a catalyst is, the more power it will produce for less fuel. So it basically means the fuel cell will be more efficient.
I think we're in a really unique position to take this all the way, to think about how we not only discover materials in a new way, how we create this platform, but ultimately how we deploy this platform in a company like Toyota to really make a difference in their business, and figuring out how we can strengthen the relationships between the company researchers, the company business folks, and the people on the ground at the university doing the discovery work would be really quite powerful, because it would allow us to streamline how we go from this called fundamental discovery process to real applications that can make a difference in Toyota and around the world.
So research partnerships between universities and organizations like Toyota are critical, because universities have the freedom to explore and have the scientific curiosity to really drive forward the frontier of human knowledge. And what we can bring to the university partnership is a concern about making the best technology we'd like. So where those two things intersect, where the interest in providing technology for society and where the frontiers of human knowledge are, that's really where we can come together and do something really valuable.
What's exciting is we don't know what the limits are. We don't know what the best performing devices and technologies that we can make can be. And so there's always this idea that there's something better out there if we just look in the right place. And so it might be that we look for a long time and never find it, but the possibility that we might is what's exciting.
Okay, so hopefully you could hear that, because what I want to do is kind of give you a feel for how we're trying to accomplish all this and take you through a little bit of the history, but also how we are accelerating this process across all fields. It's a big idea, it's a big challenge, but I think we're in a position to really do it and to do it in a grand way. And it's really fitting that I'm giving a talk to an audience in primarily, I guess, in Korea, because much of this got its start with a really talented Korean scientist, a guy named Sung-in Hong, who's at Seoul National University. He was a postdoc who worked with me, along with another postdoc named Richard Piner, who helped develop and invent a technique now that is broadly used around the world called dip-pen nanolithography. This was a technique, I think many of you are familiar with it, that really took what I would call a lemon and turned it into lemonade. We were studying water transport at the time, what's known as the capillary effect, and the fact that when you run an AFM experiment in air, water collects at the point of contact, and that water moves with the tip, and either moves up or down it, depending upon the relative hydrophobicities of the tip and substrate. And what it allowed you to do was to create metastable patterns of water that would eventually fade back to equilibrium when you remove the tip. As a chemist, when I looked at this, I thought, this is interesting, but it'd be a heck of a lot more interesting and functional if we could learn how to use it to control chemistry. And we could think of that water effectively as a solvent. And if we coated the tip with molecules that could chemically react with the surface, we could create a driving force to move molecules from the tip over or through the water to the underlying substrate to form stable monolayers. And that was the birth of dip-pen. And we started with very simple alkane thiles, you can see over on the right. And what you can see is that it acts a lot like a dip pen. You keep it in contact, the molecules continue to diffuse and the features get larger. Short times give you small features, large times give you larger features, all one monolayer high. And this was interesting because it's arguably the first additive tip-based lithography technique. And it allowed you to do it on a scale that was really interesting at the time, the nanoscale. And we began to think about it really as a desktop type fabrication tool, that we could use it to fabricate all sorts of things that were interesting on the nanoscale, including electronic based structures. And that was really the main driver at the time. That's come a long way. That was really interesting. It was really, really high resolution, had the resolution of an AFM, but it had a lot of limitations, a relatively low throughput. So we began to think about how we could accelerate the development of it and increase its utility. And so the first thing we did was, he said, if one pen works well, many pens will work better, at least in terms of printing over larger areas. And pretty soon we were building the largest cantilever arrays ever built, 55,000 a square centimeter. In fact, they became commercialized. We were about to give up on this and say, okay, we're done. We've done as much as we can do in an academic setting. Let industry run with it. And then we had an idea. We thought we could dramatically simplify this process if we took the AFM cantilever, which is effectively a glorified spring, converted into a tip that was made out of a springy material, an elastomer like PDMS, and we could mount it on a solid substrate and make many of these types of tips and effectively use all of those tips as point sources to locally deliver molecules to an underlying substrate. And that was the birth of cantilever-free scanning probe lithography in its first form called polymer pen lithography. I'm going to talk a little bit about what you can do with that in a bit, so just hold that thought. But this really changed the way we thought about doing lithography in general, dramatically simplified it, dramatically parallelized it. We were building arrays with as many as 11 million working pens, really incredible capabilities with not a whole lot of input in terms of the actual design beyond what I've described. And then we began to realize that you could drive light through the backs of the pyramids. They were macroscopically addressable, squeeze the light through the tips, effectively use it as a lens, and affect photochemistry in the near and far field. And with a digital micromirror device, you could independently control as many as 22,000 of each of these tips. And the commercial tools now, commercialized by a company called TerraPrint that we started, actually sell instruments that do just that. And so that was kind of interesting because now we could not only make structures rapidly, we could make many different types of structures simultaneously. And we began to think about these tools in a very different way. They were not only desktop fabs, which they're incredibly useful for, but they're the world's most parallel synthesis tools. So we could begin to think about using each of those tips like tiny little fingers to locally control chemistry on a surface. And that was this birth of this Megalibrary concept, this idea that you could build chips of nanoscale materials, all positionally encoded, all systematically varying in size and composition. And then that would represent an incredible number of shots on goal for new materials that might make a difference in many different fields. And that was the birth of this Megalibrary concept, and that began to drive us towards this idea of rapid materials discovery. And so I want you to think about this because, this is what I'm going to talk about is high throughput materials discovery. People have done high throughput before this talk, but they've never done it at the scale I'm going to share with you. And that's really, really important. We're talking about orders of magnitude more materials ever made before. And that's critical because if you think of the number of possibilities defined not just by the combinations of elements in the periodic table, but when you reduce a composition to the nanoscale, depending upon size, shape, and even phase structure, those are different materials. The parameter set is enormous. So this old paradigm of using really smart people to pick and look a particular structure, target structure, to make it and learn from it and then iterate on that is never going to get there. And the other thing you conclude is that we've been working with local winners as opposed to global winners, the best at that time. Most of the technologies we have are based upon materials that are the best found at that point in time. And we build an infrastructure around it. That's just the nature of the game. It's worked and worked well for many different types of areas, but it's arguably not the best way to do things. The second thing that's important is that with this Megalibrary concept, you not only can make an enormous number of new materials, but let me put enormous in a frame of context. A Megalibrary in the low end has 1 million features. On the high end has billions of features, and we've made those types of structures. Each Megalibrary has more materials than scientists have cumulatively made to date. So we're talking about dramatically changing the pace at which we explore the materials genome, but we're also talking about having a library of materials all fixed in position that we can screen and begin to collect large-scale data. And that's really critical for this AI concept because one of the biggest shortcomings of the whole move of AI towards materials discovery has been a lack of access to high-quality large data sets. And you're not going to do this with disparate data, and you're not going to do this well with small data sets. And so the question is, can we accelerate? And so this is really the challenge. And you look over on the right, when we think of the different parameter set, composition, size, shape, phase, structuring, just a few examples. I can put some confinements around those parameters over on the right. You can see some of those. You look at the numbers, these are big numbers. 10 to the 14th is a large number, and that's conservative. The numbers are actually quite a bit larger than that. We will not get there in terms of really making a meaningful dent using certainly serial and what I would call even the conventional high throughput types of processes. At least that's the fundamental thesis here. And so this is what we want to do. We want to use Megalibraries to begin to, first of all, objectively screen a particular set of parameters, figure out where the hot spots are, use that data to begin to initially train AI algorithms, and then begin to use the AI algorithms to direct us in terms of how we pursue different types of studies, and then use the patterning tools effectively as affirmation tools or not. And the hope is that we can begin to build the world's most powerful materials AI, and that would translate in principle into discoveries a lot faster and presumably at a lot lower cost. Okay, so that's conceptually what we're trying to do. Now, here's the challenge. It's not as simple as I've described it, right? There's a lot to do. Synthesis is good, and the libraries, as you're going to see, we can do a lot. We need to do a lot more, but we can do a lot. I'll talk a little bit about that. There are three silos that define this particular effort. One is massively parallel synthesis enabled by the scanning probe tools that I talked about. The second is developing companion screening tools. You need to develop these in parallel because one becomes the rate limiting step otherwise. So high throughput screening of Megalibraries is really important. How do you get the data out? How do you find where the hot spots are, where the cold spots are, where the intermediate spots are? And then how do you use that data to ultimately train and test algorithms? And I'm going to talk about all three of these in the context of this relationship with Toyota, but also outside of it as well. Okay, so how do we think about making Megalibraries? Well, we have to develop a whole new way of thinking about chemistry. So we'd like to be able to control chemistry locally on a substrate with nanometer precision. And to do that, we employ the concept of what we call nanoreactors. We basically take polymers, in this case polyethylene oxide poly-2-vinyl pyridine, load them up with metal salts, put them on tips, either a dip pen tip or a polymer pen tip, as you're going to see. Deposit the tip on a hydrophobic substrate. These are hydrophilic materials, so you end up getting a droplet that beads up onto the surface. That defines what we call a nanoreactor. The importance of that is the volume of that reactor is very, very tiny. It's attoliters to yoctoliters in volume. And then we process the reactor and heat under reducing conditions so that we reduce the metal atoms, cause them to coalesce, and then eventually blow away the polymer, so at high temperature. And we'll talk about temperatures from 600 to 1,000 degrees in certain cases. And this is kind of interesting because the reactor in this case is both the solvent and the physical confinement vessel. And the reaction is a reaction where all of the reactants, at least as I've described in cartoon fashion, go to one single product. And that's really important in terms of control. How do we know that's the case? Well, if we take tetrachloroauric acid and put that into the polymer, put it into the reactors, what you can see here are several reactors where we systematically vary in volume and size. So the diameter is going from 160 nanometers up to about 220 nanometers. These are the particle products that form 17 nanometers up to about 22 nanometers, about 1/10 the diameter. So what that shows you is increase the size of the reactor, increase the number of gold atoms, increase the size of the particle. If I reduce in size, I can reduce to tinier particles. Here you can see we're making gold particles that are 4.8 plus or minus 1/10 of a nanometer. I use that number and cite it because we've made millions of these using the polymer pen type system to generate millions in parallel. And then we can get histograms like the one shown on the right. And we can convince ourselves that this is not only a way of making these particles reliably, but I make I've developed a lot of the techniques that are used around the world for synthesizing colloidal particles in solution. It's very hard to beat the dispersity of these types of particles made because the lithography is so controllable and this reaction is so complete. And so I think I can convince you of that when I show you how we monitor these. One of the other things about I took it out of here. you can actually monitor the birth and growth of a reaction under an electron microscope. You can cool down and watch the nucleation and growth process and tease out the whole trajectory of particle formation. What you see is every atom in that reactor ends up in the particle. This is another way of showing that. If I take different salts, gold, silver, and nickel, for example, mix them up in the polymer, put them on the tips, you can see what you put in the polymer ends up in the particle. So here we've intentionally, systematically varied the nickel content in a 3-component particle from 20% to 80% as we go from left to right. The green is the nickel. The gold and silver is intentionally kept at a 1-to-1 ratio just to show the control that we have. So we're pretty much convinced in these types of reactions, what you put in the polymer reactor ends up in the particle. This, if that didn't convince you, this should. So we then began the challenges, saying, okay, let's really, making a 3-component particle is nice, but let's start making particles that are really difficult to envision making. And you certainly wouldn't want to make and spend a lot of time going through the synthesis procedure if you didn't know they had fantastic properties. So I asked a really talented grad student, Peng Chen, to go to the lab and figure out how we could make every combination of a 7-element particle. So all the single element, all the 2-element, all the 3-element, there's the ternary, the quaternary, the quinary, the centenary, and the septenary, the 1-7-element particle. In this case, keeping particle size fixed. I'll show you how we control particle size in a second to a really fine degree. This is, to me, tour de force, because one is it shows you the versatility of the synthesis technique and speed at which you can do this. The second is, when you look at this, it's really quite remarkable because the vast majority of these materials have never been on the planet before. Okay, so now beginning to make structures that we've never even considered before, certainly never made before. And that's interesting because that means we might be able to use this to rapidly discover materials that have new properties as well. If you look, these have all sorts of exotic phase structure. One of the things, if you're interested, and you can go back to the paper in Science where we published this, we use this to begin to define the phase segregation rules for these multi-component systems, which no material scientist could actually predict. I'll come back to that concept a little bit later on when I talk about the Toyota relationship, but hold that for a thought for right now. What about particle size? And can we get down to particle sizes that matter? I believe that ultimately we're going to be able to get down to single atom control. And this might convince you that we're going to be able to do that. You can't do that with the conventional polymers I talked about because there are many different sites. The pyridine groups are places where the metal ions go, and there are many pyridine groups in each aliquot of polymeric material. And so when you try to reduce the loading, you can get smaller particles, but you begin to get higher variation in particle size. So Peng Chen thought about this and he said, the way to narrow this is to synthesize polymers where there's only one group per polymer chain that can hold a metal ion. So he end-capped polymers in this case with a porphyrin group that could be loaded up with any metal of interest. And now, literally, the number of polymer chains you incorporate into a reactor will dictate the number of metal atoms that go into particle synthesis. And so now you can look over at the right. The first row are the reactors themselves. And you can see with dip pen, we can make very, very tiny reactors down to, well, you can see, I can't see the bottom here, less than 20 nanometers in size. If you look at the middle and right images, a row of images, or not row, but a column of images, what you can see is that the particles that we generate now are in the 2 nanometer, in the 6 nanometer down to the less than 1 nanometer size regime. The bottom particle, we estimate, has about 22 atoms that define it. And so you can begin to play this game. That's why I said, if you think about it, we're really pushing the limits of the characterization tools. We had to use an aberration-corrected electron microscope to actually characterize the really tiny particles. But I think this is quite interesting and is going to allow us to really study just the evolution of properties, for example, as a function of size in addition to composition as well. And if you look at the lower sets of images here, you can see that we can make mixed metal systems, platinum, copper, platinum nickel, platinum copper, and nickel here shown on the right. Okay, so what you put in the reactor ends up in the particle, even with these types of materials as well. Now that's good, but the problem with this is that it doesn't allow us to make everything in the periodic table. And in fact, we've begun to look at the periodic table and kind of considered our palette and ask, what paints can we actually use and what can't we use? So if you look at this using what I call conventional scanning probe block copolymer lithography, that's the first technique I showed you for making nanoreactors with the polytooth pyridine. You can make the structures from the elements in red. But if you want to make things from the blue, you have the issue of low volatility or hydrolyzing precursors or materials that aren't reducible with hydrogen. You have to come up with more clever ways of actually working with those materials. And you can kind of see we've color-coded them because we've actually found ways of making or using every one of these elements in this type of new particle synthesis approach. And just to give you a few examples, here, if you want to work with materials like rhodium and molybdenum, you use non-volatile organic solvents and non-coordinating polymers. That gets over some of the mobility issues, but still gives you the ability to form intact reactors that allow the metals to be reduced and ultimately to coalesce. Certain materials would react with the underlying substrates, or the substrates that we wanted to pattern on weren't appropriate because they didn't have the right hydrophobicity. For example, if we take alumina, we can modify with this perfluorinated phosphanic acid. That gets us a very hydrophobic non-stick type material that allows us to generate very nice nanoreactors. And now we can begin to move to materials like tungsten, shown below. That concept has been used over and over and over again because this isn't just about making metal particles. You can make lots of different materials. It's not clear what you can't make yet. We just know we can make a lot. So one of the things that we thought would be interesting is, could we learn how to make, for example, perovskites, halide perovskites? Well, you can't make them with the conventional polymers that I talked about, but you can take DMSO sulfolane mixtures and use that as your solvent in your reactor generation. And you can put your perovskite precursors in those, load them up on the polymer pen arrays, and now begin to use polymer pen lithography to print out literally millions of reactors. And in each of those reactors, you can initiate the reaction that leads to the halide perovskite. And so over here to the right, you can see arrays of literally millions of single nanocrystals made in this particular manner. Now, those are all the same, at least if we use all the same precursors. And there are a variety of different tricks you can use to now begin to turn a library of the same materials into a library of different materials. And one way to do that is to use a laser to induce ion exchange. In this case, we're affecting chloride to bromide exchange and now changing the ratio of chloride and bromide in the resulting structures. And you can do this with a really fine degree of control. I'm not going to go through the brutal detail of this, but here's a library of 4,000 unique halide perovskites. And you ask, how do you screen and get the information out? Well, we can look at the emissive properties of these. And from that, we found the record for blue emission using this particular approach. So this is not only a rapid way of making structures, but if you're clever, you can come up with rapid ways of getting the information out as well. Okay, what about catalysts? How do I do that? How do I think about that? I think about it in two ways. One is I can work with theoreticians that look, for example, the early libraries we make and say, which of these materials might be interesting from a catalytic reaction standpoint? We did that with Chris Wolverton. We were asking the question, could some of these be active with respect to the hydrogen evolution reaction, where their platinum is king and you're trying to beat platinum? And he can, in Computero, construct a volcano plot like the one on the left and begin to look at which of the materials that we've explored should interact well with hydrogen and might be good candidates for the HER. And in a volcano plot, you'd like to have materials at the top of the plot. And what you can see is platinum's not at the tippy top. In fact, these three component systems which we've made, platinum, gold, nickel, and platinum, gold, nickel, platinum, gold, nickel, and platinum, gold, copper, are at the top. Well, we can then go and use polymer pen lithography and make arrays of these on a glassy carbon electrode, and then begin to probe their properties. First, their structural on the right, and then their catalytic properties on the left. And what you see over here on the left is if we compare these to platinum and ask how do these compare to platinum in terms of overpotential, it's really quite remarkable. Platinum, copper, not very good. Platinum, nickel, not very good. You want to be as low as you can on this particular graph because the baseline is platinum. Platinum, copper, not very good. Platinum, gold, nickel, which if you go back to this plot, that was one of the ones he predicted is at the tippy top. It's not very good. But platinum, gold, copper is in fact as good as platinum and is a record on a per platinum atom basis, or was at the time. Now the question, of course, was why was his calculation not spot on? He predicted one, but not the other. And the reason is if you go over to the right, he modeled these as alloys. And if you look at the right, platinum, gold, copper, which is the winner, is in fact an alloy. The platinum, gold, nickel is in fact a heterostructure. It's phase segregated, and he didn't know that. And so it shows you the importance of being able to not only use computation or even AI to predict, but being able to validate ultimately by making the materials of interest and understanding the structure-function relationships at the nanoscale. Okay, so as I said, we're making all sorts of things: metal particles, metal oxides, sulfides, other types of nanostructures, halide, perovskites, quantum dots, upconversion nanoparticles. Not clear how far we can go or where we'll be limited, but we're going to explore that over the next couple of decades. What we're now doing is driving this towards mass discovery of materials that can impact primarily the clean energy industry, and hence the relationship with Toyota. So how do you do that? I haven't really told you how you make Megalibraries yet, other than the 4,000 library that I showed you. The first Megalibraries we made were made in the following way. We basically take polymeric gradients that have different metal ions in them and spray on the array of pens materials, build a gradient of materials. Flip that around. Every time you come down with a commercial tool, 160,000 pens deliver 160,000 slightly different features. Do that over and over and over again. Use time to control feature volume, and you soon can go from hundreds of thousands to millions and ultimately billions of distinct particles. We typically make about 150 to 225 million particles per library, per megalibrary. Okay, that's how you make them. How do you screen them? So here we began to collaborate with folks at the Air Force, Benji Maruyama in particular, and his crew. And we moved to them because they had a technique, a Raman technique, that could scan across a substrate and look for signatures of product. And they were interested in making single-walled carbon nanotubes. And of course, it's a great Raman signature for single-walled carbon nanotubes. So we could pattern these types of post arrays with nanoreactors, convert them into a mega library where we systematically changed composition and feature size. In this case, we're looking at gold and copper, and looking at increments in terms of composition and increments in terms of size, going from 1 nanometer to 100 nanometer. And we could then begin to expose these under controlled conditions to a carbon source, methane, for example, and begin to look at which of these catalysts were good at converting the methane at elevated temperature into single-walled carbon nanotubes. To make a long story short, this is the type of data that you get out of this. You discover a large number of catalysts. Many of these are catalysts. But if you look at this, there's only one global winner, and that's gold-3 copper. That was not known before. That was discovered uniquely through this particular process. And that's an important point because it's what I tried to say earlier. There are lots of catalysts that might do this, but there's one global winner. And most of the time, I'm convinced that we are kind of looking around the edges, and we might be completely off from the global winner or just slightly off, but we're not at the global peak. And so these types of tools, at the very least, are going to allow us to find the best compositions that work for a given reaction of interest. And that kind of takes me to the last two slides. So where are we headed with this? We now begin to want to take this data, which we represent, or we think is probably maybe the most important contribution ultimately to moving the field forward, and begin to challenge this concept of can AI begin to make discoveries that are meaningful in the materials synthesis and also in the material property arenas. And so the idea is to begin to use Megalibraries, high throughput screening, collect the data, and then begin to train AI algorithms to make predictions. And that's really how we got going with Toyota. And very recently, we took the data from that 7-element library that I shared with you, where you look at these particles. They're very exotic structures. They're not alloys, they're heterostructures, some with 2, 3, 4, 5, even 6 domains in certain cases. And we took that data and begin to train AI algorithms that we could then challenge to begin to make predictions about structures of interest. First, structures that we had made, so 4-element type systems, and confining structural outcomes to, for example, maybe 2 phases with a single phase boundary. You could argue that material scientists could make those predictions. No big surprise, the AI got it all right. But then we did something pretty interesting. We moved up to 6 elements. We basically said, give us the combinations of 6 elements in the stoichiometries that would yield not a 3-phase, 4-phase, 5-phase, or 6-phase particle, but a 2-phase particle with a single interface. It spit out 19 possibilities. We then could go to the lab, make those 19 possibilities, and structurally characterize them. And remarkably, 18 out of 19 were correct. And the reason I think this is such a landmark type of discovery and really important milestone in this whole effort is that this is no material scientist on Earth could predict this. And we have some of the best material scientists in the world at Northwestern. You just could not predict this. And I think it really bodes well for this idea of trying to begin to use this data to not just make predictions about structure, but to begin to make predictions about properties and properties of interest. And so where we're headed with this is beginning to work with groups like Toyota, but other companies around the world, and a startup company called Stoichia to begin to build what we call the Discovery Factory, and ultimately really deploy this primarily around electrocatalysis, trying to build a common infrastructure that can begin to feed these types of data sets, and all focused on trying to find catalysts, in particular things that take CO2 to value type products. Let me finish just by acknowledging the folks that have been involved. I kind of mentioned that they're in the video throughout and also throughout my presentation, but the talented group of graduate students and postdocs here, they're the ones that really make it all happen. And then funding has been provided by the Air Force, the AFRL, GSK, believe it or not, they actually sought us out for this type of stuff in the pharmaceutical industry. Kairos Ventures through a generous gift, the Sherman Fairchild Foundation, and Toyota Research Institute. I'll stop there and be happy to answer any questions if there are any. Thanks.
Thank you very much for the very interesting and impressive presentation. We have several questions, also you can refer the Q&A. Let me lead the first question. Thank you for a very interesting talk. I would like to ask, is it possible to add more than 2 different reactants separately and sequentially in Nanoreactor to explore more complicated reaction and material?
Yes, it is. In fact, you can compartmentalize and do as many as you'd like. A lot of that's just engineering and setting up the screening tools the way you would like. We often take the particles that we make and for example, pre-treat them with elemental dopants like bismuth that alloy with the materials that we generate. And then when they dealloy, this was a reaction we discovered and reported in Science 2 years ago. When they dealloy, they transform the particles from low index structures to structures with high index facets. And the reason we do that is those types of structures are the most catalytically active materials, and it gives us another level of catalytic activity that we can explore in this context.
Thank you. And the second question, what are the challenges of synthesis with nanoscale scanning group lithography, and in the mass production view, what approach could solve this problem?
Yeah, that's a good question. So I want to make a very important point. These are discovery tools. This tells you what is worth scaling. Once you discover you have to scale, and you're not going to scale with these types of printing tools. You're going to scale with conventional syntheses. So if you take that HER reaction, we found that, the world record, we published this in PNAS. We then took what we discovered and used block copolymers in bulk to synthesize the particles in solution, the 3-element particles. And then we isolated them and characterized them and characterized them in comparison to the particles we made via the scanning probe tool. And they were both qualitatively and quantitatively quite similar. So what that shows you is you can discover and then scale up and get materials that have properties that are representative of what you find in the Megalibrary. It is always, though, a challenge, right? But my point is that nobody, if somebody told you as a researcher, go make a 7-element system, I'd like you to make it in really high quality form. I don't really know if it has any good properties, but we'll figure that out when you make it. You'd want to shoot them. That's a very high bar. So it's important to find out what's worth scaling before you go through the scaling process.
Thank you. And the next question, thank you for your pioneering lecture. If the metal salt with different anions are utilized, would it affect the shape or the resultant composition when multiple metal species are coexisted?
I think it could, but not the way we've made them. So we're making materials, most of the particles that I talked about, the metal particles, are made at very high temperature. The ions don't play a significant role. Now, if you made particles the way we made the perovskites, the halide perovskites, where we're effectively using them in relatively low temperature as crystallization vehicles and confining crystallization to really, really tiny volumes, there's where you could begin to use anions and other types of materials to influence crystallization and kinetic control of crystal habit.
Thank you. And the next question, what do you see as the most important use of deep-end nanolithography?
Well, if you asked me that 5 years ago, I would tell you the most important use is in studying the consequences of miniaturization. It's primarily a research tool used all over the world by many, many labs to look at tiny structures and how does miniaturization affect their properties, or to prototype microfluidics and electronics. But today, I'd say that's important, but I think maybe the most important thing is now the world's most parallel synthesis tool. I tell the students and postdocs today, if you've worked in this subgroup, you can legitimately say you've made more materials than anybody on Earth. And that's not an overstatement. And it's possible simply because you have hundreds of thousands of tips building, synthesizing structures in parallel in defined locations with tremendous precise control over things like a reactor volume and particle size.
Okay, thank you. Then in your presentation, you have discovered and explored a number of the nanoparticles with a different composition, even including the perovskite particle and quantum dot. Then I'm wondering, is there any possibility to synthesize the metal oxide using the deep-end lithography directly?
Yes, and we published on metal oxides and metal sulfides. They're pretty straightforward, actually.
Okay,
what's coming, which is very interesting and more difficult, is how do you synthesize metals that are susceptible to oxidation? Have the audience think about that. How would you synthesize titanium, zirconium, even iron, which wants to become an oxide in metallic form? There will be papers that come out very soon that describe techniques for doing that, which we're very excited about.
Okay, thank you. Then I would like to thank the Professor Mirkin for very interesting and tremendous work. Thank you.
Thank you.